This is the Airbus A380. It is very big and heavy, weighing more than 500 tons. Have you ever wondered how this massive airplane can be lifted up into the sky? In this video, we will discover how an airplane flies. The first successful flight was made by the Wright brothers in 1903. There are three principles applied to flying an airplane: Newton's laws of motion, Bernoulli's principle, and Coanda Effect. First, let's begin with an aircraft stationary on the ground. To understand this, we can identify the four forces acting on the aircraft. The first is weight, or gravity. The second is lift. The third is thrust. The fourth is drag. Drag is the backward force exerted when the aircraft is moving forward, such as air resistance and wheel friction. Since the aircraft is not moving, there is no thrust, drag, or lift. The weight, or gravity, is simply supported by the ground. Now let's start the engine. There are many types of aircraft engines, such as turbofan, turbojet, and propeller engines. They all have the same main purpose, to provide thrust to move the aircraft forward. This is where we apply Newton's third law of motion. For every action, there is an equal and opposite reaction. In this case, the high-speed exhaust gases from the engine create a forward force on the aircraft. To understand this, think of a balloon that flies forward when you release the air in the opposite direction. The same principle applied to the aircraft's engine. The thrust generated by the engine must be large enough to overcome the drag, so that the aircraft can move forward faster. Now we know how aircraft engines use Newton's law of motion to move forward. But how does an aircraft create lift to fly? The answer is definitely the wing itself. To understand, let's focus on the wing. If you look closely at the wing's cross-section, you will find that its shape looks like this. Let's focus on this shape. At the bottom surface, you will see that the line is almost flat, while the top surface has a curve like this. This shape is called an airfoil. The front point is called the leading edge, and the rear point is called the trailing edge. The imaginary line between the leading edge and the trailing edge is called the chord line. The angle between the chord line and the relative wind stream is called the angle of attack. This angle of attack will change according to the aircraft's tilt angle relative to the wind stream. Actually, there are various types of airfoil shapes on aircraft today, depending on the manufacturer's desired design, which considers factors such as speed, maneuverability, efficiency, manufacturing cost, and others. But in this video, we will focus on basic shape of the airfoil, which is like this. Now, let's see how this airfoil generates lift for the aircraft. When the aircraft moves forward, the wind stream moves in this direction. And the same goes for the wing. As you can see, the airflow follows the shape of the wing. This is due to the Coanda effect. The Coanda effect, described by Henri Coanda in 1932, states that fluids, meaning water or any gas, tend to follow the shape of a surface. For example, if you have a water flow in a spoon, and you bring the spoon into the water flow, you will see that the flow tends to follow the curve of the spoon. The same thing happens with an aircraft wing. The airflow at the top surface follows the wing's curve, while the airflow at the bottom surface moves almost in a straight line. Now, let's replace the airflow with individual air molecules. One molecule will go over the top surface, while another will go below the bottom surface. Let's start the flow. If you look closely, the air molecule at the top reaches the trailing edge first compared to the bottom one, even though both of them start at the same time. Let's see that again. This is because the top molecule is accelerating as it passes the wing's curve due to the Coanda effect, while the bottom molecule, with no curve, moves at a uniform speed. From this, we can conclude that the airflow over the top of the wing is faster than that underneath it. Here we can see the overall wind flow past the wing. To make it clearer, we can separate the flow into layers. Here, we can see that the airflow accelerates in the yellow-colored region. Please note that this illustration is not to scale. If we zoom in really close to the surface at actual scale, we can see that the flow is like this. The flow has zero speed at the surface due to friction, but this occurs only within a millimeter thickness, so we can neglect it. Now let's go back to this flow. Here we can see that the flow on top is faster than that at the bottom of the wing. This is where we apply Bernoulli's principle. Bernoulli's principle states that an increase in the speed of a fluid will decrease its pressure. Thus, the pressure in the yellow region will decrease, while the pressure at the bottom remains unchanged. As a result, there is a pressure difference between the top and bottom of the wing. The higher pressure at the bottom will push the wing upwards and generate lift. So, this is how an aircraft's wing generates lift. Now let's return to the moving aircraft on the runway. Notice there is a small wing at the rear fuselage. This is called the elevator. The rear tip can move up and down like this. During takeoff, the elevator moves upward. When it moves up, it deflects the airflow upwards. Again, according to Newton's law, for every action, there is an equal and opposite reaction. Thus, the air that is deflected upwards will push the elevator downwards as a reaction. As a result, the aircraft will tilt like this. Remember the angle of attack that was explained earlier? Now, the angle of attack on the wing is increasing. This is the airflow with a larger angle of attack. As you can see, the airflow under the wing is deflected downwards. Again, according to Newton's law, for every action, there is an equal and opposite reaction. The deflected airflow creates an upward reaction force on the wing. As a result, more lift is generated for the aircraft. Finally, with enough lift, the aircraft can climb into the sky. Even though the angle of attack helps generate more lift, it still has a limit. This limit is called the critical angle of attack. Beyond this limit, the angle is too high, and the flow separation becomes wider. Thus, the airflow over the top will no longer move in a straight line, which we call laminar flow. Instead, the wing's surface will drag the flow, causing it to become turbulent. When this happens, there is no pressure difference, and no lift is generated. Thus, the aircraft will fall. This situation is called a stall. To avoid a stall, the angle must not exceed the critical angle of attack. In conclusion, we can summarize that the lift force generated by the wing involves Newton's law of motion, the Coanda effect, and Bernoulli's principle. The lift generated by the wing must equal the aircraft's weight so that the aircraft can float in the sky. Thank you for watching this video. Please subscribe, like, and share. See you in the next video.